Okay, so I mentioned in class today that I was going to upload this video on YouTube, and I'll put this material on as an appendix on the lecture material on D2L as well. I've done this before in class, but it's just always good to just, I think, see these things a number of times. This is about taking the square root of a complex number, and so what I'm doing here is this arises because we know we have this complex wave number equals k real plus k imaginary times I from this dispersion relationship that we went through today, which arises from electromagnetic waves propagating in a conductor. And so what I want to do to get the wave number is I have to take the square root of that number. There are two ways that I can do it. One is I can just recognize that this is an amplitude, which is the square root of k real squared plus k imaginary squared times e to the I phi, where phi is an angle with the x-axis in the complex plane. And then my square root is of length the square root of k squared, or k, and the phase angle is phi over 2. And I have plus or minus that root, which is I can take the negative root, and the way I interpret that negative root is I have a different angle that that is greater than 2 pi, but half of which is less than 2 pi. That is another phase angle for k squared. Of course, there's an infinite number of phase angles for this, but there's only 2 distinct roots, so I only need 2 of them. And then I can interpret this angle as phi over 2, and the length of this vector is k, but it's just the negative of this, and it's plus or minus the square root, right? So now, the more formulaic way, which I find more useful when we're doing things like what we're doing today, is I imagine that I have a number, a plus ib, and so that's the square. In this case, that'll be the square of the wave number, and that's equal to I want to take the square root of that square of the wave number to get but I know a and I know b, capital A, capital B, and so I want little a, little b in a root. Okay, and so the way that I do this is I just expand this square out. A squared minus b squared plus 2abi is equal to capital A plus b times capital B. Or a squared minus b squared equals capital A, and 2ab is equal to b, to make the real and the imaginary parts equal, which gives me lowercase b is equal to capital B over 2 times lowercase a. And I can put that in that quadratically looking thing on the left-hand side here, which gives me a squared minus b squared over 4a squared is equal to a. But that's lowercase a squared, capital B squared, capital A on the right-hand side. And then I just take the 4a squared, multiply it through, and I get this equation, which is actually a quadratic in a squared. And I can get the roots of that quadratic in a squared, so the two roots that are a squared, from this, which is negative b plus or minus the square root of b squared minus 4ac divided by 2a. And when I do that, I get this expression here, and then which I can simplify to 1/2 of capital A plus or minus capital A squared plus capital B squared, with that capital A squared plus capital B squared raised to the power 1/2. So that's a squared. And then what I get is a is equal to plus or minus the square root of that expression, right? And so what I have then, now I talked about this at length in lecture, but what I have then are seemingly 4 roots. I can take the root, a root that corresponds to the plus and the plus choice here, a root that corresponds to the plus and the minus choice here, a root that corresponds to the minus and plus, and minus and minus. But as I went over, that doesn't give rise to 4 distinct roots, it gives rise to 2 distinct roots. And in fact, I can get those 2 distinct roots by just saying a is equal to capital A plus square root of capital A squared plus capital B squared all over 2 raised to the power 1/2. And then b I get from b being equal to lowercase b being capital B over 2 times lowercase a. And that I get this expression here, multiply top and bottom by this expression here, and I get this expression here for lowercase b. okay? Now, as I say, there are a number of roots here, but the second root, which is distinct, is the negative of this, of what I get from a plus bi here. I can take the negative root, which is minus a minus bi. And then if I take and look at the two choices I have with the minus sign here, and I work it through, what I will find is that I get the same pair of roots, okay? So the third and fourth give the same two roots again. So what I have now is k squared is equal to mu epsilon omega squared plus mu sigma omega I. That gives me my capital A and my capital B. And then I put those in here into these expressions up top and divide through by like factor a root A out of there, where A is equal to mu epsilon omega squared. And that gives me the omega root epsilon root mu divided by root 2. That's by factoring the A out. And then that gives me a squared over a squared under the square root sign here, the inner square root sign, which is 1 plus this expression sigma over epsilon omega squared plus 1 from A over A. And then I get the same thing on the right-hand side, where the only difference is that minus sign there, which gives me this minus sign here. So it's algebraically, it's actually fairly easy to work with this. And so that's just a little bit of math for today. And I'm going to upload this. And if you know, I hope you find this useful. It's not something I can test you on, or sorry, I can test you on it, but why would I? But it's always, you know, as I say, it's good to know why we're doing what we do in the choices that we make when we go through these routes. So thank you. And as I said, have a good and safe weekend, and I will see you guys on Monday.